So next I'd like to invite David Maroney to come up. So I think as people who have been in this community for a while have seen, we've been building up some information quality expertise that started really, I think, in Santa Fe when we had some of the first information quality meetings with Greg Leptic, and Rama and David and Peng have put together this amazing, I think, last bit of our plenary. So with that, I will get your slides up, and you can go ahead and start introducing.
Thank you, Erin. Good afternoon. I am David Maroney from JPL, one of the co-chairs of the ESIP Information Quality Cluster. On behalf of this cluster, it is my privilege and honor to introduce the final plenary session of the day. I would like to start off by acknowledging my co-conveners, without which this would not have come to fruition. Rama, my longtime NASA colleague, longtime ESIP contributor, and the chair of the Information Quality Cluster, and Peng, a former JPL colleague, fellow IQC co-chair, an existing professional colleague through her work with the NOAA CDR program and other high-impact research activities at NCEI, have joined me in fostering this unique idea that has turned into the session we have right now. The primary purpose of this session is to help bring light to a topic that is so often limited to niche technical meetings and workshops, and rarely has an opportunity to be expounded upon from an interdisciplinary perspective that invites a fresh set of eyes and ears on the very real, large, impactful, and ongoing science challenges and questions in working with earth science data from observations to models. As most of us here today already know, there are very many flavors of data and information, and consequently, the quality of the information made available at our fingertips and display monitors is quite disparate from a variety of perspectives. For simplicity, the ESIP Information Quality Cluster has defined 4 high-level paradigms of information quality. These are science quality, product quality, stewardship quality, and service quality. For the sake of time, we won't go into the specifics of what each of these paradigms mean, but I will state that the often neglected component is the science quality. This is not to say it is neglected wholesale, but rather to say that the transparency and interdisciplinary cooperation of shared methods, tools, and applications are often what has kept the science quality of data relegated to, at worst, a black box, and at best, a limited consortium of experts in their respective disciplinary fields. Today represents what I consider to be an unprecedented opportunity to hear the perspectives of experts in their unique disciplinary fields of earth science research, and how they have addressed and continue to address the paramount challenges to science quality. Among these challenges is the need to consistently quantify and characterize uncertainty in the data products, as well as the need to effectively communicate what this information means to the end user, which has considerably different implications based upon the types of data, the differences in dynamic variability in certain measurement parameters, factors that determine statistical significance, and how the data products will actually be used and interpreted by the end user. Other science quality challenges include ensuring the quality control of data is transparent throughout the data lifecycle, which is often addressed through quality flagging and quality indicator variables. Since this is a panel session format, we ask that you reserve all questions after the final speaker has concluded, at which point there will be a brief period for Q&A. Since we recognize that more time will be needed for some of us who are quite interested in this topic, the Information Quality Cluster is hosting a follow-on breakout session immediately after lunch, which will consist of an introduction to the cluster, a debrief of key points raised during this session, a 4th invited speaker representing a data science perspective on numerical modeling, and a reintroduction of these 3 panelists to participate in more in-depth technical discussion among the audience. It is without further ado that I welcome you to this historic ESIP session, sponsored by the Information Quality Cluster. So Peng, my fellow co-chair, will now introduce our speakers. Thank you.
Thank you very much, David, for the excellent introduction. On behalf of IQC chairs and the members, it's my honor to introduce 3 outstanding scientists to you today to talk about data uncertainty from 3 very different perspectives. And Dr. Karen Collinson is a senior scientist and climate scientist from Woods-Hole Oceanographic Institution. She wears many hats, and one of which is the co-chair for Decadal Survey. And she's going to talk to us a little bit about the importance of uncertainty, data uncertainty associated with data. And the second speaker is Dr. Amy Biberman from JPL, Jet Propulsion Laboratory. She's a principal statistician. Sorry, I'm a little nervous. She's the founder of the Advisory Committee on Climate Change Policy and she's going to talk to us about why should we need data uncertainty information? Why should we care? And Dr. Isela Simpson is a climate modeler from NCAR, National Center for Atmospheric Research, and she's in the climate analysis section. And she's going to talk about the impact of data uncertainty to models. So as David has mentioned, each talk will be about 10 minutes or less, and please hold your questions to the end. We'll have a Q&A session. The IQC chair, Rama, would facilitating that session. Now, let's welcome our first speaker, Dr. Collinson.
Hi, Peng, thanks. They asked 3 scientists, and then she had the audacity to say that the talks would be 10 minutes or less. I can assure you they won't be less. Well, you've had lots of time to look at my beautiful campus. Let's just talk about some thoughts that I have about information that's needed about the data. And with 10 minutes, I really don't have time to go into too many different aspects of it, so I thought I'd focus a little bit on uncertainty. And uncertainty, the way that I'm talking about it here, and which is often used in our field, describes the doubt that we have about the quantity that we're measuring, given the results of some measurement that we have, and then our estimate of the error distribution of that measurement, which is distinct. I'm making a distinction here between that and the quality of the data, which I think of as complementary information, which could be a number of different things. Certainly, it would be great if it had the confidence of the uncertainty estimate as part of the quality. So if you have a very poor estimate of the uncertainty, that might give you one quality flag. But a high uncertainty doesn't necessarily mean that it should have a bad quality flag. So that there is a lot of value in having data that, even though it may have high uncertainty with it. Other quality of data issues could be conditions violating the retrieval, or measurement assumptions that you're making as you're doing it. Many other quality flags come to mind. And there are other additional uses of uncertainty, which I think some of my co-talkers are going to mention: data assimilation, comparison of data with models, and so forth. And so I'm not going to touch on those. So I'm going to go just. I think the best thing I could do for this talk is to mention just a few very specific examples, some things that I happen to have been involved with. So something that I have a chance at least of understanding and explaining well. Peng is part of the NOAA Climate Data Record Program. I have a data set that I produce from there that's the near surface air temperature, humidity, and winds over the ocean with an SST. And then the most important piece of that is then the calculation of the surface fluxes of turbulent, sensible, and latent heat flux, so therefore evaporation as well. And I just put this up here because this is just the mean values from 1 year from that data set. But we use SSMI, SSMIS data, we use series data, we use GPCP data. We're ingesting data from many, many different sources. So we're already moving into sort of this combined network in order to create some more data content. As part of this, we did estimate uncertainty for every single data point. We have a 3-hourly, 25-kilometer data set from 1988 through 2000, and now we're into 2017 in it. And every point has an uncertainty estimate, and we can talk more about that offline if you would like to know how we actually did that. But what I'm showing here is a 10-year mean. So in the middle panels, you can see the latent heat flux, the actual values that we have, and then the total uncertainty. And you can see, so it's very different depending on where you are. Notice the western boundary currents, for those of you who aren't oceanographers, that would be the Gulf Stream and the Kuroshio, pop up really nicely on that. And then we have sort of a global uncertainty estimate from that, which is about 10% for latent heat flux and about 25% for sensible heat flux. So one set of comparisons that I've worked on with this is with Graham Stevens. This is a paper in 2012 in which we put together many, many different data sets and made an estimate of the global heat budget. Now, if the Earth were not warming in any way, shape, or form, we know that should be zero, that we should all sum to zero. So the fact that it does not in our data sets tells us something about where we are in actually measuring these variables. Of course, the Earth is warming a bit, so the surface imbalance is about 0.6 watts per meter squared. So the key here is that when Graham and others of us put these together, there was a little bit of an ad hoc kind of, well, I think there's about this much error in this piece, and this much error in this piece, and this much, and so we'll kind of adjust the different numbers to make things work. The next route that we took was to actually take the closure when we close the budget. So if you look on the top left, it says the net absorbed was 16 watts per meter squared. That's when we took all of the data sets regarding the surface fluxes, the atmospheric fluxes, the top of the atmosphere, radiation, rain, evaporation across the globe. When you put all of these together and sum them up, they came to about 16 watts per meter squared, which should be a little bit less than 1. That's our imbalance in our data sets. Okay? But because we wanted to do a little bit of a more quantitative adjustment to get the number down to about 0.5 or 0.6, we actually forced all of these data sets to come up with an uncertainty estimate, and then used a quantitative minimizing cost function, looking at uncertainty estimates of each individual flux to come up with a final set of numbers. And so actually on the bottom right is the final, one of the final sets of numbers from that particular example. If you look at it in the mean water budget, this is one of the reasons I like to look at, there's a very commonly quoted one, which is from Kevin Trenberth, which is in the yellow from 2011. And then our original numbers are in white, and then the adjusted numbers are in blue. And the key thing here is that because we had uncertainty estimates, we could actually make a quantitative way of adjusting the different numbers. Now, one of the things I do like to point out with this one is the other great thing about this, having uncertainty estimates, and the uncertainty estimates from these different communities were not quite all derived in the same way. There's at least one uncertainty estimate, which shall remain nameless as to which one it is, that literally they didn't have a number and we kept pressing them. They're like, okay, 10. Oh, shoot, did I? No, sorry, no, I didn't. Yeah. Anyway, so, but it was, but I like to look at this because, for instance, one of my friends, Eric Wood at Princeton, does the river runoff. And he was so excited because he called me up one day and said, we have better river runoff numbers, Caroline. We can help constrain the evaporation budget. And I'm on 3 minutes. And I said, Kevin, would you mind looking at these numbers again? Your river runoff is at 50, and these are in cubic kilometers per 1,000 cubic kilometers per year. My estimate of uncertainty in my evaporation is almost the entire river runoff across the globe. So, you can adjust yours a little tiny bit and it doesn't really help me at all. Another example, the use of uncertainty for future missions. And I'm not going to talk about, what results we're coming up with on the decadal survey, but let me just give you a couple of ideas about the ways that uncertainty can help us. How do you define what are the greatest scientific needs? When you have 1 million science questions out there, when you're sitting on a panel with a bunch of climate scientists with every possible background and discipline, how do you decide what are the most pressing needs? Well, one way that you could use to do that is to ask, where is the largest uncertainty in the questions that we need to answer? Okay? Because that would say, if we only have X billion dollars to spend on something, maybe the biggest bang for our buck is to hit the things with the highest uncertainty. If you don't have an uncertainty estimate, how do you, it's much more difficult to try to make some differences like that. And that's just a figure from IPCC showing where the uncertainty ranges are. Then another point from that is that you also need uncertainty targets, sometimes to set quantifiable goals. How do you know if you've designed a satellite mission that's going to give you a better estimate? It's not enough to write a science question that says we need to understand better the role of the atmospheric circulation in the polar regions and the polar teleconnections. That's not enough. We need to be able to say our uncertainty of this quantity is X, and we think if we can set these constraints on our measurements, we can reduce that uncertainty by Y. So without uncertainty estimates, your data set may not be as useful as you might think in terms of where we could go next, what could be happening next. I'll conclude with just two thoughts here. First off, this is a very complicated plot on the right, but it's the possible changes in the Earth system and at what warming degrees that might happen. And you can see that's uncertainty there as well. How much does the Earth have to warm before these different things happen? The next question is, when are we going to reach that warming? Because of all that uncertainty, when I go talk to companies and when I go to DC and talk with people, one of the things that I like to talk about is the fact that that uncertainty costs us a great deal of money. Okay, because uncertainty is a clear impediment to successful adaptation, a quote from the Stern Review. If you have urgent and unplanned for adaptation, that's very expensive. But if you do adaptation too soon, if you invest in assets too soon, that's also economically bad. So one of the things that we can talk about is you can now start to relate what your economic advantage is by talking about what is the uncertainty costing us. So this is what I'm going to talk about in the oh, yeah. I swear I haven't heard that since I was a grad student. Oh, I'm having flashbacks for finishing my PhD. So this is something that I'll talk about more in the afternoon session. That's why I just want to leave you with this slide. But I have some thoughts on the best practices for data users, including concepts like including quantitative uncertainty information with the data set. It is not good enough to tell your users there's a paper out there somewhere that tells them something about the entire data set in general. And that's just not enough. Uncertainty information should be per data point. Quality flags I mentioned. Documentation should include error information, how you calculated the uncertainty. Propagation of errors should be used when aggregating data. And when you validate your data sets, you should be validating both the data itself and your uncertainty estimates as well. So I'm just going to leave you with that, and thank you very much.
Okay. Thank you very much. I think that was a great talk, Carol Ann. If anybody's wondering, I'm the recycling symbol. If you're looking for me, I'll be out there at lunchtime. 10 minutes, as Carol Ann said, is not really enough to say very much, although she said quite a lot. I'm basically going to give you a glorified, regurgitated version of the abstract. We've been thinking a lot about uncertainty quantification at JPL since we got a new director named Mike Watkins, whose interest in the topic predated his appointment as director. And we've especially been, thanks to the people on the Orbiting Carbon Observatory mission, been actually trying to implement uncertainty quantification methodologies for their retrievals for every data point, as Carol Ann suggested. Okay, so I said in the abstract, the title of the talk is something like, what is uncertainty, where does it come from, and why should you care? So I'll just go through those. Data uncertainty, so that's what we think of when we open up our data file and we go to use the data product for some scientific analysis that we have. And you can think of the data uncertainty as telling us something about the relationship of the numbers that are in the file to the true values that nature produces for the quantity of interest. And the scientific method, it's always been my perspective that the scientific method kind of teaches you that the way science works in a cartoonish kind of way is that we formulate hypotheses and then we test them against observational evidence. And these data files that are being produced and that we're talking about here are that observational evidence. So we formulate a theory. Often we make predictions using that theory by running a model of some kind. And then we compare the prediction of the model to the observations of the data or what's in those files. But so we kind of need to know, since the data in the files are not what the real world is necessarily doing, but they're kind of an approximation of it, we need to know how good an approximation that is if we're going to turn the crank on our hypothesis, test it, refine it, test it, refine it, and so on and so forth, which is how things proceed. So I use the word ignorance rather than doubt, but I think it gets to the same idea. So we could think of data uncertainty as being the remaining ignorance that we suffer from even after we've seen the data. Where does it come from? Well, it comes from various sources. If we're talking about remote sensing data, which is what I've been thinking about mostly, I think probably everybody in this room knows, but out in the world they don't necessarily know that there is no thermometer in space. All space-based observations are snapshots of spectra. And those spectra are then downloaded to the ground and processed heavily to turn them into what amount to inferences about what the true state of the atmosphere is. And like any inference, if you took a statistics class, you probably know any inference is kind of comes with you think of it as a point estimate of the quantity of interest and a confidence interval around that point estimate. And there are many reasons why, Carol Ann just said them all, I won't even bother talking about why we need them, but we need to have them and they need to be produced at the time the data product is produced. It just doesn't make sense to try to go back and do it after the fact. A lot of people ask me, well, isn't validation uncertainty quantification? And I say, well, it is if you believe that the number of locations at which you had ground truth is representative of all the conditions that are represented in your data set. And that, for some missions, that's somewhat true, and for most missions, I think it probably isn't. You have a few ground measurement stations for OCO2. You have 7 stations around the world where they're actually looking at ground-based CO2, and they're attempting to infer from that what the uncertainty on millions and millions and millions of observations are in places that are unlike any of those 7 places. To make a long story short, data uncertainty arises because there's not a one-to-one relationship between what we observe, those spectra, and the true state of the atmosphere. Often you can imagine you have to do a lot of processing on those radiances to turn it into that state, and it often requires some ancillary information. So why should we care? Carol Ann also said this already, because scientific conclusions drawn from the data and the analysis that we do, or decisions that are made, like adaptation decisions or mitigation decisions, have a cost. It costs if you do it. It also costs if you don't do it. And what we really ought to be doing is we ought to be looking at the uncertainty in our conclusions and then deciding our action on the basis of the prospective costs under the conditions that are given to us by the data that we have, incorporating the uncertainty. There's a whole discipline on this. It's called decision theory or game theory that has bulletproofed this down to quantifiable results. In order to put that into action probably requires a bit more work because it's a quite mathematical endeavor, but nonetheless it exists. So I assert that probability is probably the best way out there to measure data uncertainty. Probability is, I call it, say, coherent. It's internally consistent. It's guaranteed that you won't get nonsense because it's math after all. The idea of error propagation through this chain of processing that lead you to data, and then further along through a chain of analysis to a conclusion, everything has to be coherent. It can't break the laws of mathematics. You can't end up with 2 + 2 = 3. And if we were to all agree on a universal definition of uncertainty in terms of probability, then things would be comparable across data sets, across analyses, and across questions. If everybody makes up their own definition of uncertainty, which isn't quite true now, but it tends to be a little bit in certain areas, then there's no way for one analysis to build on another, because the uncertainty reported in this analysis doesn't have the same meaning as the uncertainty reported in that analysis. Probability is also a pretty intuitive concept. If you're talking to non-scientists and decision makers, everybody, I think, gets the idea of should you take your umbrella if I tell you there's a 40% chance of rain today. There you've incorporated the idea of cost into the decision you're going to make about whether to take your umbrella or not. I think we already talked about number 3 there. Probability is mathematically precise. It's the basis for hypothesis testing and decision theory. I already talked about that. That's it. So I'm done, even with 3 minutes to go. Oh, thanks. I told you it was a glorified abstract, and I have a lot more to say, but that can wait till this afternoon.
All right, so thanks a lot to the session organizers for giving me the opportunity to speak here. So I'm Isla Simpson, and I'm an atmospheric dynamicist at NCAR, and I work a lot on evaluating global climate models. So the perspective I'm typically coming from is I'm trying to evaluate the representation mostly of large-scale dynamical processes within the atmospheric component of global climate models. And so when it comes to comparing with observation-based products, there are some issues that we face. So one is the quality of observation-based products, which I guess is a large part of what this meeting is about. And I'll freely admit right now, I don't typically worry about this too much. I'm the kind of user who just takes observation-based products and assumes that they're pretty much okay. But I think for many of the fields that I'm looking at, that's probably a valid assumption, and we have a large number of data sets we can look at, make sure we get the same answer. But the issue that I worry about a lot more is that we only have a limited sampling of the real world over the short observational record. So we don't necessarily know the ground truth that we're trying to compare our models to. And this is a big issue in the coupled ocean atmosphere system, where there's a large amount of variability on many different timescales, and your signal to noise ratios can be very small, and aspects of even the climatology can be pretty uncertain over the short observational record. So I think this issue has really been brought to the forefront recently with various large ensembles of model simulations that have been done, where you can really see the variability that can be present given a limited record. But I think it's still an issue that is continually underappreciated in our field and often not adequately dealt with. So how can we deal with this issue when it comes to trying to evaluate global climate models? Well, one thing we can do is to combine the use of large ensembles of model simulations with appropriate statistical analysis of the observations to understand what are the limitations of our short observational record, and to identify where can we say that our models are in error or where they're good, and where do we just not have sufficient information from the real world to do that. Another way we can deal with it is to take a more process-based view of model errors. So look at things like short-term drifts from initialized forecasts and look at how processes start to go wrong. And I think both of these are good approaches, but here I'm going to talk about the first of these, so combining the use of large model ensembles with the observations to evaluate our models. And so in a short talk, I'm obviously going to have to gloss over a number of the details here, but I'm going to talk about this in one particular example, and that's the Northern Hemisphere circulation response to El Nino Southern Oscillation. So since I'm glossing over the details, this work came out this year. If you're interested, or I'd be happy to talk about it with people after. So this is where it was done with Clara Desser, Karen McKinnon, and Adam Phillips, all at NCAR. So as you're probably all aware, ENSO is our kind of dominant mode of variability in the coupled ocean atmosphere system. It's an irregular but quasi-periodic variation in sea surface temperatures in the equatorial Pacific. Most people are familiar with the warm phase, known as El Nino, and then the cold phase, known as La Nina. And so we typically define ENSO events based on sea surface temperatures in a region in the equatorial Pacific. And so I'm going to use the Nino 3.4 region, which is shown in the red box here. We do a bunch of stuff to that time series to get some kind of normalized index of sea surface temperature variability in the equatorial Pacific. And I think with the observation-based products, we can pretty safely go back to about 1920. So that's the time series of sea surface temperatures here. And so we define El Nino and La Nina events as being years where the sea surface temperatures lie outside of plus or minus 1 standard deviation. And so over this record, going back to 1920, that gives us 18 El Nino years and 14 La Nina years to look at. So I'm going to show the composite mean difference between the 18 El Nino years and 14 La Nina years. So here's the difference in sea surface temperature between El Nino years and La Nina years. And this is accompanied by sea level pressure anomalies over pretty much the whole of the Northern Hemisphere. So on the right here, you're seeing the sea level pressure anomalies that accompany El Nino events as compared to La Nina events. And this kind of gives us the canonical picture of how El Nino affects the large-scale circulation. In particular, it gives us this deepening of the Aleutian low here, and then there's kind of sea level pressure anomalies in the North Atlantic, reminiscent of the negative phase of the North Atlantic Oscillation. So these large-scale circulation changes, they have impacts on precipitation and temperatures. If you live on the West Coast, you probably have some kind of view of how El Nino affects your weather for a given winter. So it's obviously something we want to get right in the models, and we were interested in evaluating this. And so to do this, we looked at a bunch of simulations with NCAR's Community Earth System model. And the simulations we're using are what are known as pacemaker experiments. So this is where we're simulating the fully coupled ocean, atmosphere, land system, but with the exception of one region in the equatorial Pacific where we nudge the sea surface temperatures towards the observations. So basically in this region here of the global climate model, we're basically making the sea surface temperatures follow what has historically happened. And so our model is experiencing the same sequence of El Nino and La Nina events as what happened in the real world. So we have 10 of these pacemaker ensemble members, because that's the advantage of using a model, is you can have multiple realizations. And these members differ only in the initial conditions. So a very small random noise perturbation is imposed in the initial conditions. And then the members evolve differently, basically according to the butterfly effect and the random weather noise that results from those different initial conditions. So we've got 10 perfectly valid realizations of the real world from our model. So we want to see whether the model captures this sea level pressure response to El Nino that we've seen over the observational record. So here's our first pacemaker ensemble member. So remember, this model has experienced the same El Nino and La Nina events as what has happened in the real world there. So you might look at this member and say, well, the model looks like it's doing a reasonable job. Maybe it's got too big of a response here in the Aleutian Low, not quite enough going on in the Atlantic. But then you could look at the second pacemaker ensemble member, which looks pretty different from the first. So it has a weaker Aleutian Low response, maybe more going on in the North Atlantic. And then you can look at all 10 pacemaker ensemble members, and you can see the kind of diversity that can exist in our response to El Nino within the model. So you can pick out 2 members that have pretty different magnitudes of the Aleutian Low response there. Or you could pick out 2 members that differ a lot in the North Atlantic. And so if our model is realistic, we could say, well, we could have easily sampled this sequence of events plus noise in the observations and not seen anything going on in the North Atlantic. Or we could have equally sampled this sequence of events plus noise and had the conclusion that El Nino really affects the North Atlantic. And that's because there's uncertainty associated just with the internal variability to the system that you're not really getting a complete view of with just a short observational record. So if the model has a realistic representation, then these kind of ensemble members can give us a view on the uncertainties that exist, because there could be uncertainties that you can't necessarily see given your limited observational record. And obviously, this is a very important if. We need to accompany analyses of these kind of model ensembles with analysis of the observations as best you can to ensure that they're kind of both sampling from the same distribution, so that the uncertainty that we see within our model is representative of the uncertainty that's present in the real world. And without going into the details, I would believe this is the case for this El Nino composites. You can do bootstrapping analyses on the observations and show that the variability is similar. So to summarize, observations are obviously vital for assessing the fidelity of our climate models, but with a limited observational record, even going as far back as you can to the beginning of last century, aspects can be pretty uncertain. Just even basic aspects of the climatology can be uncertain, and we may not be fully aware of the uncertainties because we can't see all the timescales of importance. Ideally, we'd like to have longer observational records, and I guess that will happen in time. But I think also large model ensembles can provide valuable insights into the uncertainties that are present on our observational record, provided that they're realistic and the variability within our models is representative of that of the real world. So I think the feedback can go both ways. We can kind of identify the limitations of our models from observations, but we can also become aware of uncertainties that are present in the observations with our models, because we can have much longer time series and capture all the different timescales of variability that you can't necessarily see in the short observational record. Obviously, it has to be made sure that the variability in the model is realistic in any of these analyses. So we'll leave it there. Thank you.
Well, thank you all for very inspiring talks, and we have a few minutes for questions. We'll take the first question from the Slido. Can redundant or dense measurements, particularly those from sensor webs, help reduce uncertainty? So who would like to take the question?
I'm tempted to say yes or no,
Ask a scientist.
depending on the uncertainty in the sensor web data. I mean, it's just another source of data, and the more data you can combine intelligently to get a complete picture of the phenomenon of interest, the better off you are. But I would note I've done a fair amount of work in the problem of data fusion, which is the combining of satellite data sets and presumably other sources of data as well. And the weighting, effectively, that you end up applying to combine sources of different sources of information has everything to do with the uncertainty on those individual sources. So you can't do that without uncertainty on the individual data sources.
Yeah, and I would just agree that somehow I find a lot of people think that it really is just a matter of getting more measurements solely. Why are we not all, they were asking why don't we have people standing out on cruise ships with their phones, taking temperature measurements and sending those back to us. And yes, that would give us a lot more data, but that's where you get to the discussion of uncertainty and say that actually is so much more uncertain than the data points that we already have, that even if we had a quadrillion of those data points, that's not helpful in beating down the uncertainty in our measurements. And so I think that really getting people to understand the concept of uncertainty and that sheer numbers of very uncertain data is not as helpful as you might think, is a useful thing that we can be communicating with people.
And you won't actually know that unless you know the uncertainties on those uncertain data points.
That's correct.
Right? So it might be worth having people stand out on the cruise ship with their cell phones, even if they're collecting crappy data, as long as you know it's crappy. Right? As long as you know what the uncertainty is.
Well, let's see. I'll go to the next question here. Have we ever used uncertainty analysis to realize that we are using inappropriate or ineffective tools or approaches?
I would say yes and no, probably. No pun intended. I mean,
this is why we're losing the climate science war, by the way. The public.
I think part of it is vocabulary, right? The word uncertainty is a squishy word that I think really needs to be better defined. And I have a slide or two about that for this afternoon. But people mean the word uncertainty to mean different things, and that really needs to be pinned down if we're going to answer questions like that.
Let's go to questions from the audience.
Yeah, hi, thank you very much for whoever organized of not having a male-dominated panel, yet another male-dominated panel. I've been thinking about the communication of uncertainty, or rather your talks have been making me think about that. And we always hear about it in the context of climate, right? And people think, oh, well, it's so, those scientists don't really know, so how do we? And when you try to explain it to them in the context of science, and most people aren't scientists, and they just kind of get confused and whatever. So I was wondering if there's any way that we could start showing normal people about all the uncertainty in their daily lives, focusing on other things like, say, the length of your commute time and how uncertain the guess of that might be for your next commuter. I'm sure there are other examples, and I don't know yet what they are, but I was wondering if you had any thoughts on that.
I do some consulting with different companies, and I remember the first time we were doing some basically forecasting for them, and we were very ginger about it because we didn't want to just give them a forecast. We wanted to give them a description of the likelihood of variability and so forth, and so we were so gingerly talking to them, and they said, oh, you mean like a probability distribution function? Oh, yeah, we can handle that. Our models can handle that. We understand that. And we said, oh, well, then we're good, because that's really what I wanted to give you, was sort of that example. And so I think that there are many people who do have an understanding of that, and it's the way that we're saying we're uncertain about the results. Because sometimes we're not very careful about the numbers, right? We're uncertain about, it's much better, I think, to say something about, we're uncertain about exactly what year the Arctic sea ice is essentially going to not be present in the summer. We have a range of years from, and I don't know what that's not my area of expertise, I should not have picked that example. But we say, let's say we have, basically between all the different model runs, there's maybe at least a decade of difference between those. But we have it kind of down to a decade. So we're not completely helpless. We just make it sound like we're totally uncertain, and so therefore we can't say anything. I think of what we say is, this is an event that is coming. We have an uncertainty. We don't know if it's going to be, it could be anywhere between 2025 to 2045, 35? 25 to 38. Oh my goodness. So we have a 13-year gap. That changes, I think, when I talk to people and they understand that when we're saying we're uncertain, it doesn't mean we don't have a clue. It means we have a clue. We just haven't pinned down we can't give you a date for it. Or we might not have identified every single variable associated with it, which gives us some uncertainty, but it doesn't make us uncertain of the laws of physics. It doesn't make us uncertain of the laws of radiative transfer. So I think it's more just saying, here's what we're uncertain of. And I think when they realize what it is that we're uncertain of, they'll realize the uncertainty is not some basic uncertainty, right? It's more of a very precise kind of meaning.
Yeah, I think that would be pretty helpful to have come up with some examples. I guess like examples of things that are kind of outside of anything you've sampled. Like that seems like a big issue. Is that often we have extreme events and people are attributing it to global warming and these things happen. We just maybe have not sampled it in our short record. So I think it's difficult to make people aware of that. People can often get confused when you have an extreme event in one year, people attribute to global warming, and then you have an extreme kind of opposite sense the next year. I think it's difficult to make people realize without looking at the data themselves how variable things really are.
One more?
So as a co-organizer of this session, I have a question unless there's anybody else who has a question. So Amy and Caroline touched on this in their talks regarding remote sensing principles and things that could be done to potentially reduce uncertainty in the actual observation systems. So can any of you touch on what are some novel cutting-edge technological advancements that we might be able to leverage to reduce the fundamental uncertainty of the actual observation systems themselves?
So observation system is a combination of the instrument and its sampling pattern and the technology that the instrument uses to measure the radiances and its measurement error characteristics and its resolution. But in earth science, it's been my experience that by far the largest contributor to uncertainty of what we call data that we make available to the public are the retrieval algorithms. There are some sensors do have significant measurement error issues. That's, how much error is there when I measure a radiance in a particular channel? But most of the instruments that I know anything about are pretty good that way. And where almost all the uncertainty comes from is in other assumptions that are made during the retrieval algorithm or in computational artifacts of solving to minimize a function on a discrete grid. There are lots of things that we could do. One of the things we're doing at JPL a lot of right now are Monte Carlo studies, Monte Carlo simulations with those retrieval algorithms where we do what a lot of people are familiar with the concept of an observing system simulation experiment. Where we changed its name and called it an observing system uncertainty experiment, which we call an OSU instead of an OSI, right? And the idea there is to feed in synthetic known truth that is realistic. Of course, it's not going to be the actual, because if you knew that, you wouldn't be doing any of it in the first place. But you try to make it as realistic as possible. You use a forward model to turn that into a set of radiances. You push those radiances through the retrieval algorithm, and then you got something out that claims to be representative of what went in. And if you do that over a large ensemble of things you put in, you can get a distribution of what comes out, and that gives you some understanding. Now, what I think is really important to understand is that an exercise like that is aimed at quantifying the characteristics of the algorithm, of the observing system, or the retrieval algorithm itself. In statistics, we talk about the statistical properties of an estimator, like the sample mean. The sample mean is an unbiased predictor of the true population mean, and its uncertainty, if you will, its variance goes down as the square root of n if the things you're putting in are independent. Well, those are two operating characteristics of that computation that is to compute the mean. It's not a statement about the uncertainty of the thing that comes out, of what the estimate is. It's a property of the machinery. And so our point of view is that if we can characterize the operating characteristics of our machinery, then we know something about how much to trust what the machinery produces. So I'll take this opportunity to pitch that idea. There are also many more sophisticated ways of doing that inference than the way it's typically done with a least squares fit or even an optimal estimation retrieval. There's something out there called Markov chain Monte Carlo, which is another way of trying to understand what the distribution of the true quantity is given what you observed in the radiances. And right now that's too computationally intensive to be practical for an operational mission. But people are looking into how to speed that up, and there's even an aspect of it. One reason I asked the question of Jennifer was because I think there's a whole area of research to be engaged in here that would involve a lot of people in this room that I've started to call the theory of data systems, which is a catchy name that appeals to JPL management. And I think of that being the study of how the movement of data, or let's call it the topology of a data system, where the nodes are that have the data, where the users are, where the computational facilities are, what the costs of moving data around or reduced versions of the data around are, how all those costs trade off against the uncertainty in the final product.
I think we're running late into the lunch hour, so let's thank our speakers one more time.